Welcome to White Space. How big is the cave system hiding under the moon's surface really? Put this on in the background. Close your eyes if you want and let the story carry you. Let's begin. In September 2023, the Indian lander Vikram touched down on the lunar surface near the South Pole. It was the first soft landing in history near the polar region of Earth's satellite. The Pragan rover rolled out onto the regolith and over 14 Earth days traveled approximately 100 meters, detecting sulfur, aluminum, calcium, iron, and titanium in the soil composition. Then the lunar night came. The temperature dropped by 270 degrees over the course of several hours. The craft fell silent and never woke up. Nevertheless, India became the fourth country to successfully land a spacecraft on the moon and the first to do so near the South Pole, right where it is coldest, darkest, and where, in all likelihood, lies what will make everything else possible. The word satellite applied to the moon somehow sounds modest. The moon does not simply travel alongside Earth. It determines how our planet exists. It is the lunar gravitational pull that shapes the tides of the world ocean, providing rhythmic mixing of water and nutrients. It is the moon that stabilizes the tilt of Earth's axis within a range of 22.5 to 24.5 degrees. This seems like a negligible oscillation. But Mars, lacking a massive satellite, tilts within a range of 10 to 60 degrees over millions of years. On Earth without the moon, climate zones would shift rapidly and catastrophically. The emergence of complex life would have been significantly more difficult. The moon has existed alongside us for nearly as long as Earth itself. 4.5 billion years in that time. It has not spoken a word, yet has told us a great deal. The very first human calendar was lunar. Ancient peoples noticed that the appearance of the night luminary changed with strict periodicity and counted months by full moons long before they learned to write. The moon was the first celestial body toward which a human aimed a telescope. Galileo in 1609 saw its craters and mountains and drew a conclusion that sounded bold for its time. The moon is a world, not a perfect celestial sphere. Then 3.5 centuries passed, and we sent people there. But let us return to the structure of the moon itself, because it is remarkable. The satellite is arranged quite asymmetrically. The side facing Earth is covered with dark basaltic plains, the lunar maria. The far side is almost entirely a cratered highland terrain with very few maria. Why this happened, scientists spent decades figuring out. One version: in the first millions of years of the moon's existence, its Earth-facing side remained hotter due to tidal heating. The crust there was thinner, magma broke through to the surface and flooded the lowlands, forming basaltic plains. The far side cooled more quickly, the crust thickened there, and there was almost no volcanic outpouring. In the end, we see one moon, but effectively two different landscapes depending on which side one looks from. There is another asymmetry that took a long time to explain. Large meteorite craters and basins are concentrated predominantly on the far side. For a long time, this was attributed to observational bias. The visible side, it was said, had simply been better studied, but orbital spacecraft data confirmed it. The distribution is uneven. One modern hypothesis links this to the fact that in the early solar system, Earth partially shielded the near side of the moon from the flux of large objects. This remains only a hypothesis for now. There is no definitive answer. A close approach to these landscapes was made possible by the Grail mission, two small spacecraft that NASA launched in 2011 under the names Ebb and Flow. They flew in tandem along lunar orbit, continuously measuring the distance between themselves to micron precision. Where denser rock lay beneath the surface, gravity pulled the leading spacecraft slightly more strongly, and the distance between them changed by negligible fractions of a millimeter. From these variations, scientists reconstructed a map of the Moon's internal structure with precision inaccessible to any other method. The result surprised everyone. The crust on the side facing us turned out to be significantly thinner, in some places only 20 kilometers. On the far side, its thickness exceeds 70 kilometers. Furthermore, the Grail mission discovered a vast network of solidified magmatic dikes, vertical rock formations that formed when molten rock under pressure forced its way through cracks and solidified. The Moon in its youth was far more active than its current dead appearance would suggest. In December 2012, the mission ended. Both spacecraft were deliberately directed into an unnamed mountain near the North Pole. Before impact, they expended their remaining fuel so as not to contaminate the lunar surface. A modest end for two spacecraft that had created the most detailed gravitational map of any body in the solar system, including Earth. Now about craters. They cover the surface of the Moon so densely that new craters lie on top of old ones, and still newer ones on top of those. This is an archive of impact events spanning 4 billion years. On Earth, most ancient craters have been destroyed by erosion, tectonics, and biological activity. On the Moon, they have not. There is no wind, no water, no tectonics, and impact leaves a mark forever. Consider the crater Tycho. It is located in the southern highlands. Its diameter is about 85 kilometers, its depth nearly 4.5 kilometers. Tycho is young by lunar standards, approximately 109 million years old. This is precisely why its ray system, bright streaks of material ejected by the impact, is still clearly visible even through a small telescope. The rays radiate from the crater for thousands of kilometers across the entire visible disk. And at the center of Tycho rises a peak about 2 kilometers high. This is a characteristic feature of large impact craters. At the moment of impact, rock under pressure behaves like a liquid. It springs back upward, forming a central mountain massif. This process completes within minutes. Then everything solidifies, and we see a scene frozen in stone forever. If one calculates the formation time of Tycho on the geological timescale, this crater formed in the age of the dinosaurs. By lunar standards, it is nearly new. No less remarkable is the crater Aristarchus. It is one of the brightest objects on the lunar surface. Its walls reflect sunlight almost twice as efficiently as the surrounding regolis. For centuries, this region was a source of mysteries. Beginning in the 18th century, observers recorded brief luminous events there, the so-called lunar transient phenomena. Flashes, changes in brightness, hazy patches. Sir William Herschel reported such observations in 1783. Their nature has not been definitively established, though most researchers lean toward the hypothesis of gas release from the interior. The Aristarchus Plateau is rich in pyroclastic deposits, traces of ancient volcanic eruptions, possibly volatile compounds preserved beneath the surface still periodically find release. The Moon has long not been a volcanically active body in the conventional sense, but calling it definitively dead is also not possible. There is yet another landscape on the Moon that for a long time attracted no attention at all, the so-called rills or grooves. These are long, sinuous depressions resembling dried riverbeds. Some extend for hundreds of kilometers. They are clearly not of impact origin. The contours are too smooth, the banks too even. These are traces of lava flows that once moved beneath a solidified crust, which then collapsed. The very structure that in another context is called a lava tube. There are hundreds of such rills on the lunar surface. This means that lava tubes beneath the surface may be significantly more numerous than the isolated ones discovered to date. Beneath the lunar surface lie even more intriguing structures. In 2009, the Japanese orbital spacecraft Kaguya discovered a hole in the ground approximately 65 meters in diameter in the region of the volcanic Marius Hills Plateau. the vertical shaft descended to a depth of no less than 80 meters and opened into an underground cave, a lava tube. In 2017, radar from the same spacecraft confirmed beneath the surface in this region there exists a tunnel at least 50 kilometers long and up to 100 meters wide. The cave's walls have remained intact over billions of years. Inside, a stable temperature of around minus 20 degrees, no radiation, no temperature fluctuations, no dust raised by the solar wind. This is not merely a curious geological fact. It is a potential home for the first lunar settlers. Nature did part of the work for us 4 billion years ago. The comparison with terrestrial lava tubes is extremely instructive in this case. On Earth, such structures reach 30 meters across. On the Moon, several kilometers. On Mars, about 250 meters. The difference is determined by gravity. The weaker the pole, the higher a tube's ceiling can rise without collapsing under its own weight. Lunar gravity is 6 times weaker than Earth's. This allows cavities of a scale to exist that would be impossible on Earth. And this is a direct consequence of the fact that the Moon is small. Its mass is just over 1% of Earth's. In 2009, NASA conducted one of the most spectacular experiments in the history of lunar science. The IL-Cross spacecraft deliberately crashed into the crater Khazau near the South Pole. A 2-ton upper stage struck the surface at a speed of about 2.5 kilometers per second and ejected a plume of dust and vaporized material nearly 10 kilometers high. The probe that followed behind passed through this plume, analyzing its composition, and also struck the Moon 4 minutes later. In those 4 minutes, water vapor was detected. Not traces, not indirect evidence water. More than 100 kilograms of water ice per ton of soil in the permanently shadowed regions of the crater. This changed everything. The Moon ceased to be an absolutely dry world. Where did the water come from? Most likely it arrived here over billions of years with comets and water-bearing asteroids. In addition, some water may have formed directly on the surface. Protons from the solar wind interact with oxygen contained in the regolith and produce water molecules. In illuminated areas, solar radiation immediately destroys these molecules. But deep within polar craters, where sunlight never reaches, the temperature drops to minus 240 degrees Celsius. This is one of the coldest places in the solar system, colder than the surface of Pluto. There, ice is preserved indefinitely. This is precisely why Vikram landed near the South Pole. This is precisely why subsequent missions are aimed at the same destination. And this is precisely why the first serious conflict over lunar resources may flare up there. The area around the lunar South Pole is small. Zones of permanent illumination, ridges and peaks of craters where the sun shines almost continuously occupy an area of a few square kilometers. These are Malapert Peak, Nobel Ridge, and several other elevated features. Zones of permanent shadow are somewhat larger, but also localized. Locations where there is simultaneously both access to solar energy and proximity to ice deposits are literally a handful. Whoever installs equipment there first gains an enormous logistical advantage. The Outer Space Treaty of 1967 prohibits national appropriation of the Moon, but does not regulate resource extraction. The Artemis Accords, developed by NASA beginning in 2020, established their own system of behavioral norms. But they are not an international treaty and have not been ratified by a number of major space powers. In this legal gray zone, several states and private companies are already maneuvering simultaneously. The Moon did not promise to remain neutral territory forever. But let us return to what lies not on the surface but beneath it and even deeper. In 2019, scientists working with data from the Lunar Reconnaissance Orbiter and the Grail gravity mission published a result that made planetary scientists stop and read twice. Beneath the South Pole Aitken Basin, the largest impact crater not only on the Moon, but in the entire solar system, an anomalous mass was discovered. The basin has a diameter of about 2,400 kilometers and a depth of 8 kilometers. The total elevation difference from the floor to the rim is 16 kilometers. This is a structure visible from Earth with the naked eye as a dark spot near the southern limb. The anomaly extends to a depth of more than 300 kilometers and weighs, according to calculations, about 2 quintillion kilograms. For comparison, this is approximately 5 times the mass of the Hawaiian Islands. There are 2 versions explaining the anomaly. The first, the metallic core of a giant asteroid that struck the Moon 4 billion years ago, has still not sunk into the lunar core and remains in the mantle. Computer simulations show at a certain angle of impact and velocity, the metallic core of a body can indeed become lodged in the mantle and not descend further. The second version, a high concentration of iron and titanium oxides formed during the cooling of the ancient magmatic ocean and settled in precisely this region during crystallization. Which of these is true or whether both are partially correct will only be determined by drilling, which remains a very long way off. Now about things that are visible right on the surface but long remained unexplained. At several dozen locations, the lunar soil is covered with bright, sinuous patterns, lunar swirls. The most well-known of these are Rainer Gamma, the Gaina magnetic anomaly, and the swirl in the crater Einga. These structures are not topographic formations. The surface there is just as flat as the surroundings. The soil is simply brighter. The width of some swirls is several tens of kilometers. Their nature is connected to local magnetic anomalies, where the magnetic field is stronger. The solar wind carrying charged particles is deflected and does not reach the surface with the same intensity. Regolith protected from particle bombardment darkens more slowly. It simply does not have time to age within the same time frame. This discovery carries an important implication. The Moon once possessed a global magnetic field. About 4 billion years ago, a planetary dynamo operated in its core, the same mechanism that still protects Earth with its magnetosphere. Then the Moon cooled too much, the liquid portion of the core solidified and the dynamo stopped. The Moon was left without global protection. Only the memory remained in the form of magnetized sections of crust and bright patches above them, like scars from a long extinguished shield. Moonquakes occur on the Moon. This is no longer a hypothesis. It is a documented fact. Seismographs installed by the Apollo expeditions from 1969 to 1972 operated in continuous recording mode until 1977, when the program was wound down due to budget constraints. Over those 8 years, several thousand events of 4 different types were recorded. Deep moonquakes occur at depths of 700 to 1200 kilometers under the influence of tidal interaction with Earth. Much as the Moon causes Earth's tides, Earth deforms the lunar interior. Shallow moonquakes occur near the surface. The cooling crust contracts and cracks like dried clay. Thermal moonquakes arise at dawn when the surface heats rapidly after a 2-week night. Impact moonquakes come from meteorite strikes. Data from these seismographs allowed scientists to reconstruct the internal structure of the Moon. It has a solid inner core with a radius of about 240 kilometers, a liquid outer core with a radius of about 330 kilometers, a mantle and a crust. The structure resembles Earth's, but the proportions differ. The core constitutes only about 20% of the Moon's radius, compared to 54% for Earth. This is a direct consequence of the Moon's origin. Most of the metal went to Earth during the collision with Theia. There is another type of record on the Moon, far less straightforward to interpret. These are boulder tracks. The Lunar Reconnaissance Orbiter photographed thousands of such tracks. A boulder rolls down a crater slope, leaving a clear trail in the regolith. Since there is no wind on the Moon, these tracks are preserved unchanged for millions of years. Unless a new impact or moonquake occurs, by the freshness of the track edges and by how much subsequent regolith has dusted over them, scientists determine the relative age of the event. One documented case, inside the 138-kilometer crater Antoniadi, a track from a boulder over 15 meters in diameter was recorded. The rock rolled more than a kilometer and stopped at the edge of a small secondary crater. Had it traveled another 75 meters, it would have landed right in the center. On the lunar surface, one can also find traces of human presence. The descent stages of the Apollo lunar modules still stand on the surface. The Apollo 17 rover, the last human-operated vehicle, left a track nearly 35 kilometers long. The footprints of astronauts in the regolith have not been erased. Without an atmosphere and wind, there is no mechanism to destroy them. In 1,000 years, they will look the same as they do now, unless a meteorite strikes precisely that location. The Lunar Reconnaissance Orbiter photographed the Apollo landing sites from a height of 30 kilometers, obtaining images with a resolution of about half a meter per pixel. In these images, the descent stages, equipment, cables, rover tracks, and even pathways of footprints are visible. These are not circumstantial evidence, these are photographs, now about color and temperature. The true color of the lunar surface is dark gray, almost black. The Moon reflects only about 12% of the sunlight that falls on it. For comparison, fresh asphalt reflects about 4%. The Moon is slightly brighter than asphalt, which is precisely why at full moon it shines brightly enough to cast shadows. If its surface were white like snow, nights on Earth would be almost like day. Thermal conditions on the Moon are extreme by any measure familiar to someone accustomed to Earth. On the illuminated side, the surface heats to 123 degrees Celsius. On the shaded side, including permanently shadowed craters, the temperature drops to minus 240 degrees. The differential is nearly 400 degrees. No atmosphere to smooth out these extremes. The lunar day lasts about 13.5 Earth days, and so does the night. The dark patches on the lunar surface, the lunar Maria, occupy about 17% of the total area and are concentrated predominantly on the near side, where they cover nearly a third of the surface. These are solidified flows of basaltic lava that spread 3 to 4 billion years ago. At that time, the lunar crust was heated by impacts from large objects during the so-called late heavy bombardment, a period when the current orbital architecture of the solar system was established and many objects were ejected onto new trajectories, colliding with planets and satellites. After the bombardment, magma poured into the gaps of the shattered crust. It slowly cooled and solidified. Today, these are flat, dark plains over which early astronomers were predictably bored, preferring to examine the more dramatic craters. The lunar Maria were given romantic names long before anyone knew what they actually were. The Sea of Tranquility, the Sea of Rains, the Ocean of Storms, the Sea of Fertility, the Sea of Serenity. These names were given by Giovanni Battista Riccioli in 1651 in the belief that the dark areas were actual bodies of water. There was no water there, of course, but the names remained. And it was in the Sea of Tranquility that Apollo 11 landed in July 1969. The Moon did not form from a cloud of gas and dust around the young sun, as happens with most planetary satellites. According to the most widely accepted theory today, the giant impact hypothesis, about 4.5 billion years ago, a body roughly the size of Mars struck the young Earth, a planetesimal given the name Theia. The collision was not head-on, but glancing at an angle of about 45 degrees, Theia was destroyed. Most of its iron core, being denser, sank into Earth's core. The silicate debris ejected into space from both Theia and Earth's mantle gathered under the force of gravity and over several million years formed the Moon. This is precisely why it has a disproportionately small iron core. Nearly all the metal remained on Earth. This is precisely why the isotopic composition of lunar rocks is so close to Earth's. The Moon is literally a part of Earth blasted into space and reassembled. This theory originally predicted that the Moon should be completely dry. During the collision, all volatiles, including water, should have evaporated into space. That was the thinking until ice was discovered in the south polar craters. Today, scientists suppose that a small amount of water may have survived even the collision trapped in very deep interiors, or may have arrived later with comets. The theory is plausible in its broad outlines, but the details continue to be refined. After its formation, the Moon was much closer to Earth. Back then, it would have appeared 15 times larger in the sky than it does now. The tidal forces it generated were many times more powerful. Earth rotated on its axis significantly faster. The initial day lasted about 6 hours. Lunar tides gradually slowed this rotation. The Moon, in turn, receded in accordance with the laws of conservation of angular momentum. This process continues today. Each year, the Moon moves away from Earth by approximately 3.8 centimeters. This has been measured to millimeter precision using laser ranging. A laser beam from Earth reflects off retroreflectors left by the Apollo expeditions and returns. The distance is calculated from the travel time to centimeter accuracy. Thus, the human traces on the Moon, which seem like silent relics of the past, continue to serve as a highly precise scientific instrument half a century after the landing. In a few billion years, the Moon will have receded so far that total solar eclipses will cease. The disk of the Moon will no longer exactly cover the disk of the Sun. The coincidence we observe now is pure chance. The Moon is 400 times smaller than the Sun, but 400 times closer to us. No laws of nature stand behind this. It is simply luck. If life exists elsewhere in the galaxy, and if it has reached the level that allows looking at the sky and asking questions, then few such beings are likely to have drawn a similar lucky ticket. The question of how many satellites Earth has seems elementary. 1, the Moon. But this is not entirely accurate. Earth's gravity interacts with other objects, creating systems of temporary and semi-permanent capture. These are negligible dimensions by cosmic standards, but real structures likely existing for as long as the Earth-Moon system itself. They are sustained by a constant influx of interplanetary dust particles from meteor streams and the interplanetary medium. The mechanism is simple. Dust particles drift through space, fall into the gravitational trap of a Lagrange point, linger there for some time, then under the influence of perturbations from the Moon or Sun leave the trap and are carried away. New particles arrive in their place. The cloud exists as a permanent structure, even though the individual dust particles within it are constantly changing. It resembles a river. The water in it is always different, but the river remains. Besides the dust clouds, Earth is periodically visited by so-called mini-moons, small asteroids that Earth's gravity temporarily captures into orbit. In 2006, asteroid 2006 RH120, about 7 meters wide, remained in geocentric orbit for 18 months. The first documented case of long-term capture. Asteroid 2020 CD3 was captured approximately in 2016 and remained Earth's satellite until March 2020, nearly 4 years before gravitational interaction with the Moon placed it on a heliocentric orbit. These objects are not visible to the naked eye and are discovered only through targeted searches. How many of them are orbiting Earth right now, unbeknownst to anyone, is unknown, most likely at least one. There are also quasi-satellites, asteroids, that do not orbit Earth in the strict sense, but move around the Sun along an orbit so close to Earth's that from our perspective they trace loops near our planet. Asteroid 3753 Kruithne, discovered in 1986, has been following such a trajectory for thousands of years. Its orbit around Earth in a reference frame tied to our planet resembles a horseshoe. From a heliocentric perspective, it simply travels along nearly the same orbit as Earth, slightly ahead or behind. Several such objects have already been found. There may be many more simply small and dark eluding observation. Lagrange points are not merely theoretical objects from celestial mechanics textbooks. They are genuinely functioning gravitational niches. The James Webb Space Telescope operates at the L2 point of the Earth-Sun system, 1.5 million kilometers behind our planet, in Earth's permanent shadow. This allows the telescope to maintain an operating temperature of about -230 degrees and conduct observations in the infrared range without interference from solar heat. Several solar observatories have been sent there as well. The L4 and L5 points of the Earth-Moon system are being considered as potential sites for orbital stations and transit nodes. A spacecraft at such a point expends almost no fuel to maintain its position. This matters when every kilogram of fuel costs millions of dollars to deliver. The resource map of the Moon looks as follows. Regolith in polar regions contains water ice, a potential raw material for drinking water and rocket fuel through electrolysis. Water is split into hydrogen and oxygen, from which high-quality rocket propellant is produced. The ability to produce fuel directly on the Moon radically changes the economics of distant missions. Instead of bringing everything needed for a flight to Mars from Earth, one can refuel at a lunar station. The surface is rich in aluminum, titanium, iron, and silicon. The creep terrain regions concentrated near the ocean of storms contain high concentrations of thorium, uranium, and rare earth elements. There are about 34 such zones on the Moon, each roughly 80 kilometers in size. And finally, helium-3. This isotope is virtually absent on Earth, since Earth's magnetic field deflects the solar wind that carries it. On the Moon, over billions of years, it has accumulated in the upper layers of the regolith. The concentration is low, 1 gram per 100 tons of soil. But total reserves, by the most conservative estimates, amount to several 100,000 tons. Helium-3 is one of the potential fuels for the fusion reactor of the future. The deuterium-helium-3 reaction produces significantly less neutron radiation than the standard fusion reaction. Making a reactor simpler to build, controlled fusion is not yet commercially viable. But if it becomes viable, the Moon will become the largest energy deposit in accessible space. These are all arguments in favor of a lunar base. The counter-arguments are also weighty. The cost of delivering 1 kilogram of cargo to the lunar surface at current prices amounts to several $1 million. A human in lunar conditions requires daily air, water, food, medications, and spare parts for the spacesuit. In the event of critical equipment failure, evacuation takes days. Lunar dust is one of the most aggressive materials that technology encounters. The particles are sharp-edged because there is no water or wind to smooth them. They are electrostatically charged, cling to everything, penetrate mechanisms, scratch visor glass, clog ventilation. Apollo astronauts reported problems with regolith after just a few hours on the surface. Permanent human presence means permanent war with this dust. The question is not whether the Moon should be developed in principle. The question is what it actually costs, who will pay for it, and what exactly they will receive in return. While these calculations are being made, orbital spacecraft continue their work. The Lunar Reconnaissance Orbiter was launched in 2009 and by the mid-2020s had spent more than 15 years in lunar orbit, a record for interplanetary spacecraft. In that time, it created a map of the lunar surface with resolution down to half a meter, measured the radiation environment at every point of its orbit, compiled temperature maps of polar regions, found outcrops of bedrock in fresh craters, recorded thousands of boulder tracks, and photographed the Apollo landing sites. The data from this spacecraft will keep scientists busy for decades of analysis. The Chinese spacecraft Chang'e 4, which landed on the far side of the Moon in January 2019, became the first lander in history to reach that region. Communication with Earth required a relay satellite, Khazau, positioned in the Lagrange L2 orbit of the Earth-Moon system. It is this satellite that provides the radio link between the lander and ground stations. The Yutu-2 rover operated on the surface for several years, making it the record holder for longevity among all lunar rovers. In the von Karman crater within the South Pole Aitken Basin, it discovered unusual mineral mixtures in the regolith that did not fit standard models of lunar geology. This may be ejecta from deep layers exposed by the impact that formed the crater. Analysis is ongoing.
Chang'e 6, launched in 2024, accomplished a fundamentally new task. It delivered soil samples from the far side of the Moon. Until then, all samples brought back from the Moon by the American Apollos and Soviet Lunas had been taken from the near side. Soil from the far side differs chemically and isotopically in a number of parameters.
Comparing the two sets of samples makes it possible to understand precisely how the geological history of the two hemispheres differs and to test models built on orbital data. The question of lunar colonization exists on two parallel levels. The first is technical, how to actually do it. The second is why. For the technical question, there is an answer. Robots first, humans later. First, autonomous drilling rigs extract ice and produce water. Then 3D printers construct shelter walls from regolith. Then humans arrive at a prepared place, not an empty field. This is precisely the current concept of the agencies and companies working in this direction. This is not science fiction. These are specific technical programs with specific timelines and budgets. None of these timelines has yet been met, but work is progressing. For why, there are several answers and they are not equal. The scientific value of permanent human presence on the Moon is debatable. Robots are cheaper, risk no lives, work around the clock, and require no return ticket. The strategic value is different. Presence on the Moon means access to resources that may, in the future, determine the balance of power in space. The industrial value is a fuel base for distant missions. The symbolic value is presence where others have not reached. Every state and every company weighs these arguments differently. The lunar race that ended in 1972 has resumed. But now a dozen players participate, not two. The Moon has been with us from the very beginning. It regulated our tides, our calendars, our sleep cycles. Studies show that human sleep is synchronized with lunar phases, even in people living in cities isolated from direct moonlight. It was studied by Galileo and Newton, Euler and Laplace. 12 people walked on it, all Americans, all men, over a period of a little more than 3 years. More than half a century has passed since then. Not a single person has traveled farther than low Earth orbit. This is perhaps one of the strangest pauses in the history of human exploration. Nevertheless, every few years a discovery appears that compels a reassessment of what seemed definitively established. An anomalous mass beneath the South Pole. Caves extending for dozens of kilometers, traces of an ancient magnetosphere in the form of bright swirls. Water where no models predicted it should be. The moon readily shows us new questions every time we think we have found answers to the previous ones. This is the quality of the best teachers. The next several years will yield more data than all the preceding decades combined. Spacecraft with new instruments, missions tasked with drilling into those very polar craters to a depth of several meters, crewed expeditions that will be able to retrieve samples from depth and deliver them to laboratories. If everything goes according to plan, people will return to the moon as early as the late 2020s, and in the 2030s perhaps stay there for several months. To make this happen, engineers are solving right now the challenges that must be solved: radiation shielding, management of regolith dust, life support in conditions of extreme temperatures, reliable communication from the far side. This is a good time to be interested in the moon. It is not going anywhere, although strictly speaking it moves a little farther away each year, by 3.8 centimeters, at roughly the same rate that fingernails grow. Quietly, methodically, as everything connected with the moon tends to do.